Welcome to part 3 of the op-amp trilogy. In today's video we are talking about different types of op-amps and some characteristics you might want to consider when choosing one. Different types of op-amps. There are many different types. In the world of op-amps we can get different selections and whatnot, but they each have their own categories, I'd like to say. We have general purpose ones, where you could probably use them in your own hobbyist circuits and whatnot. An example of this will be the 741. So this is a very general purpose op-amp. It's not used for any specific purpose, and this is why they are suitable for hobby projects or short-term projects you might have. We then have precision op-amps, where they are specifically designed for high stability, low offset voltages, low bias currents, and low drift parameters. Of course, I am just skimming over these and just giving you a flavor of what these different type of op-amps are being used for. We have programmable ones, which are programmed using a set current for a desired attribute or characteristic of the op-amp. These are mainly used in low power applications. I believe some of them you can code them. Single supply op-amps, so yes, op-amps can come in single power supply, and we could just connect the negative end to ground. So they do exist, and that is quite beneficial, as it can be a pain to get, a negative power and a positive power. And audio amplifiers. Audio amplifier op-amps, as the name suggests, they are for audio related purposes, and this is what they exist for. A common one would be a LM386, sorry, so that's LM386. I do plan to show a simple audio amplifier circuit, but this one would be a nice one to start off with. Moving on to common op-amp characteristics. These are things you may want to take into consideration when choosing an op-amp for your project. I'm going to list a few here and briefly explain them. Supply voltage. This goes without saying that you should take into consideration your supply voltage and see if your op-amp is able to be powered with it. As mentioned before, there are single supplied op-amps out there, so keep in mind that these do exist. Another one would be frequency response. The ideal response would be infinite, and the op-amp will amplify all frequencies equally. Though in practice this is probably not so likely. Op-amps do have a wide and variable bandwidth, and because of this I'll draw a brief graph. Just a little example here. So let's say we have voltage gain, then we have our frequency. So let's say that's 1 Hertz to, I don't know, 10 million Hertz, I suppose. This graph isn't scale, but you get the point. We go up to 120 decibels. So for voltage gain wise, a specific frequency, maybe our op-amp is doing quite well, and it will start to decrease. This is the frequency response of the op-amp. So if you have higher frequency applications, maybe this would be a good characteristic to keep in mind, because your voltage gain will drop off. Open loop voltage gain. So with no feedback, an op-amp will respond to different frequencies in terms of gain. And when mentioned, open loop gain refers to the maximum AC gain at very low frequencies. How much gain would this, with AC gain, would this occur at very low frequencies? Something else to keep in mind. Maybe wondering, is there a closed loop gain? Yes, there is. Closed loop voltage gain. So this is when feedback is present. We have spoke about feedback in our previous videos. Please do check them out. A level responsive gain can be produced from a variety of frequencies, and this comes with the added benefit of reduced noise and distortion. That's always a positive. Gain. Bandwidth product. What is this? It is a term often used to describe the possible combination of gain and bandwidth. Still a bit confusing, isn't it? So for example, if I had 140 kilohertz bandwidth, output as BW, multiplied by a voltage gain of 10. So this is our voltage gain. This would result in a bandwidth of 1.4 hertz. So this is our gain bandwidth product. So it's a bandwidth times our voltage gain, we get our gain bandwidth product. So what would we use this for exactly, this gain bandwidth product? We can determine the maximum gain we'll be able to get from a desired frequency, essentially. So by doing this, if we're working on certain frequency, we would want to know what's the maximum gain we can achieve from this. Input offset current. So I've just removed all the previous listed characteristics, but I will put them at the end of the video for you to see. So what is this one? Ideally, the two inputs into an operational amplifier, current-wise, would be 0, usually. However, we have mentioned before that this is actually extremely small. And because of this, unequal current will cause a different voltage at the inputs. This small difference in voltage will be amplified and thus cause the output to be other than 0, which is not so ideal. This input offset voltage can be applied to correct this, and be applied between the inputs to correct the output. So just from this explanation, you can already see how useful and important it is to know this. We do not want our op amps to produce unrealistic or unfavorable signals, voltages, and so on. So we want to know what we're putting in and what we're getting out. Input offset voltage. But yes, so this is the same as the current except with the voltage. You do produce some tiny little minuscule voltages, and you do not want that to affect your output. But anyway, back to temperature coefficients. So these two, input offset current, input offset voltage, are affected by changes in temperature and tend to drift higher as temperature increases. So do keep that in mind, and do keep where you're going to place your electrons in what temperature conditions. Last but not least, slew rate. The slew rate can determine how fast an op amp can change into relation to how fast the output voltage can change. And this is a response to an immediate change in voltage at the input. So the higher value of slew rate and the faster the output can change, the more easily it can reproduce high frequency signals. So I'm going to go over a graph here. I'm going to draw something out about what I meant by just that. So say we have a signal coming in, we have a change of voltage, and we're going to get this, essentially. Change of voltage again, we're going to get this. So this is a uncompensated output. So as you can see, it did not change so fast, as it was kind of like shifting up and down before it realized that this is the actual output. It came back again, it did that, changing up and down. So the faster the output can change, the more easily it can produce high frequency signals. So I'm going to draw a compensated output now. I have here, and actually you just go like that. So this is a compensated output. So as you can see, it's not perfectly like straight here, this is our rise and fall times here. So rise and fall times. And this is how a compensated output would look. Obviously I would think this is much more preferable over the uncompensated output. You don't want to have this like noise jumbling going on here. And yes, that about covers the common op-amp characteristics. I will now show you the summary of all of them. So here's a brief summary page of everything. Of course there are more characteristics when it comes to the op-amp. These are just a few I've labeled off here just to give you a flavor of what some characteristics are. You could of course have a look. If you want to do another video on these to go more in depth, please feel free to let me know. And that's it I have covered for the op-amps. Next video wise, I will be doing that audio amplifier and some practical notes on what to do with this. So I hope you've learned something, and take care.